pretty good.
All right, so we've been talking about nuclear energy, nuclear decay, and so forth. And in the last 125, 130 years, scientists have learned how to use and harness the energy that's released when radioactive isotopes decay. And that's what we're going to talk about. So first of all, question with this? Don't worry, let's just focus on this. So you read about two things in the article that we read earlier in the week. Fission versus fusion. What does fission mean? Fission. Rosalind? Yeah, fission means to split something. And so nuclear fission is when a large, unstable atom decays and splits into two smaller atoms. Okay? And so in this diagram, what you see is uranium-235, a large, heavy atom, being impacted here by a neutron. And in the process, transmutating quickly into uranium-236, which then quickly decays into krypton and barium, and in the process releases 3 more additional neutrons. This is nuclear fission. A large radioactive nucleus splitting into 2 much smaller nuclei. And so that's what's being shown here. Neutrons impacting a uranium-235 nucleus, which becomes unstable and breaks down. And this is the basis for the generation of electricity using nuclear power, as well as the use of nuclear weapons, this idea. Another way to sort of write this is in an equation form. It means basically the same thing. Okay? What you have is uranium-235 with the addition of a neutron, decays into barium and krypton, and also neutrons as well. And it's typically uranium-235, which is used in nuclear reactors. Uranium found naturally is usually uranium-238. A smaller percentage is uranium-235. And when you read in the article about the nuclear fuel cycle, you know that uranium has to be enriched. It has to be separated into uranium-235 to be used as a nuclear fuel. Maria?
On the last element.
Yep.
On the last page. The 2 and 1 0.
Yes.
What
Neutrons. Those are neutrons.
Oh, okay. Thank you.
And so we know that this process releases huge amounts of energy. Who's the scientist that helped us to understand this? Michael?
Albert Einstein.
Yeah, Albert Einstein. And Albert Einstein, as you probably have seen, developed this equation, E equals mc squared, which is actually pretty simple. What it says is that energy is basically interchangeable with mass. They're sort of 2 sides of the same thing. And mass can be converted into energy. And that's what happens in these nuclear reactions. Okay? And energy equals mass times c, which is the speed of light, squared. And what this really translates into is a very small amount of matter, if converted into energy, results in a huge amount of energy. Okay? And that's why energy released by these nuclear reactions is so great. Now, there's a couple of things to know about this nuclear fuel and these nuclear reactions. first of all, when we look back here at this uranium, this is a single uranium atom. If we have many uranium atoms, a neutron impacts this uranium atom and it splits, releasing what? Besides the krypton and barium?
Neutrons.
More neutrons, which can then do what? Hit other uranium-235 nuclei, causing them to split. And then that releases more neutrons, which hits more uranium nuclei, causing them to split. And we have what we call a chain reaction. Chain reaction is a series of repeated reactions that occur rapidly and which are sort of self-sustaining because the products of one reaction cause another reaction to take place. This is a really neat way to illustrate it in this video. This video sort of simulates that using mouse traps. So let's check it out. So a bunch of mouse traps set with ping pong balls resting on them. Nice.
Oh my god. Can we watch that again?
So again, the result of one decay, if you want to call it that, it releases a ping pong ball, which hits another mouse trap, which causes it to release more ping pong balls. And you have this sustained chain reaction. And there's a couple views of it you'll see here. And once that ping pong ball, the first one, is dropped in there, it's sort of random when it's going to trigger the next one, but eventually it reaches that point and the reaction is happening very, very quickly. Now, imagine the same experiment, but I only had 2 mouse traps in that plexiglass container. And I dropped the ping pong ball in there. Am I assured that they're all going to go off? No. The first ping pong ball might not hit any, it might come to rest. Even if it hits one, that next ping pong ball might come to rest, not impacting the other one. Okay? This can help you understand the idea of critical mass. It takes a certain amount of the fuel source to reach a critical mass to continue this reaction and allow it to be self-sustaining. Okay? Thus. And so without that critical mass of atoms, okay, then the chain reaction is not sustained, does not continue. And nuclear energy uses that concept of having a critical mass to allow for the nuclear reactions to take place at the proper speed. Now, if that nuclear reaction, that chain reaction, is unregulated and uncontrolled, it can result in the rapid release of energy, okay, all at one time. And that's the principle behind nuclear weapons. So nuclear weapons were devised in the 1940s during World War II. It's actually sort of a race between the United States and Germany. Both countries were working towards the development of nuclear weapons, and both were getting pretty close. Okay. The United States developed and refined their nuclear weapons first. Okay? And the United States is the only country which has used nuclear weapons in war twice. Okay? So there's not many countries, there's several countries that have obtained nuclear weapons and developed them, but they've only been used by the United States. And the 2 times they were used, both at the end of World War II, okay, both dropped in Japan. The first, the name of the atomic bomb was called Little Boy. Okay, it was dropped in Hiroshima, Japan. The second was Fat Man, dropped over Nagasaki in Japan. And this was at the end of World War II, and after the bombing of Nagasaki, that led to the surrender of the Japanese and the end of the war. So let's just talk a little bit about the two types of. So the United States. Do you know what the name of the group that was researching this in the United States? Michael? Yeah, it was called the Manhattan Project. They were researching how to use nuclear energy to make a weapon. Eventually coming about with a couple different designs, testing them in the desert. Okay, and they had two sort of different concepts about how a nuclear weapon could be devised. Using uranium-235 as the main fuel. This is Little Boy, and this is the one over Hiroshima. And it used, first of all, a conventional explosive, just a regular explosion, which would send a small uranium bullet forward in the weapon, which eventually impacted a larger mass of uranium in the front of the weapon. And that impact forced the uranium to have a critical mass and to start that chain reaction that we just talked about. Okay, because again, you need that critical mass. Okay, the Fat Man was a different design. The Fat Man used plutonium as its main source, and it was basically a large sphere, hollow sphere. Okay, inside of that was another sphere of plutonium. Okay, and what happened on the outside of this large sphere, they had conventional explosives all wired together so that they would all explode at the exact same time. They all explode at the exact same time, causing this hollow sphere to implode and get smaller, forcing the plutonium into a smaller size, causing it to reach critical mass and then start the chain reaction that expends all of that energy. So just to give you a concept of how much energy is released, okay, it's a huge amount. The bomb, this aerial photograph shows the city of Nagasaki. Okay, the top one is before detonation of Fat Man. Okay, you can see obviously a city, you can see the river. And after ground zero, where this weapon was detonated, is just on this side of the river over here. And you can see what the city looks like after that bomb had exploded. It just is completely decimated. You know, within the narrow range of where that ground zero was, basically you have just destroyed everything, completely destroyed. All life completely destroyed within that radius. As you move out from that radius, so things died from the impact, from the explosion. Okay, buildings were destroyed from the explosion. The release of energy basically vaporized people, animals in that area. As you move out from the center where the detonation happened, those forces are less, but you also have then the radiation, okay, which caused radiation sickness and death after that. And as the farther, obviously the farther you go away from where the atomic bomb was detonated, the less those impacts become. But you have huge amounts of radiation released in the atmosphere. Rosalind?
So I have two questions. So one of them was, what are those boxes on the ends of the bombs?
Those were just for the flight, to help with the aerodynamics of when they dropped these. They were dropped out of airplanes, really large planes flying extremely high over Japan. What were they called? I forget the name of the type of plane it's called. But anyway, they drop them from very, very high in the atmosphere. They're set to detonate when they get to a certain spot. I believe Hiroshima detonated Little Boy detonated on impact, where Fat Man was exploded over Nagasaki, and then the blast goes down.
God bless the person that was like
Flying the plane.
Geez, like what was
Yeah, they were not affected. They survived. They just got, they were high enough in the atmosphere that the explosion doesn't affect them. What was your second question, Rosalind?
So why were like most of the scientists in Germany Jewish?
Well, so lots of scientists studying nuclear energy that were Jewish were fleeing the Holocaust, and some of them came to the United States and did their research to help thwart German advances during the war. Lucas?
I have two questions as well. When the bomb dropped, so there was no bodies, right, in the blast, in the grounds?
Not in the immediate area. I mean, there's, I don't even exactly know the story, but basically people in that immediate vicinity are sort of vaporized. There are also stories about their shadows being preserved on the ground in certain areas. Yeah, there's certain books written by survivors that were in sort of obviously not right at the vicinity, but there's some pretty gruesome effects of these weapons.
Also, the ground looks sort of flat. Is that just the area?
Yeah, this was probably not like that immediately after. It was probably taken after some of that debris had been cleared. Yeah, Michael?
So like, is it true that they're actually like some like when people went back, like the clay was like really really fertile from all like the.
I don't know. I would doubt it, but I'm not sure if the soil would be fertile.
And so like just looking at like the two designs, like it seems as though like the little boy is like way more simpler, but all it really is just like firing up the lab target.
Yeah.
But, like Fat Man is like a bunch of explosions causing that. Is that just like?
Yeah, it was just two different ways they had, ideas they had of how to do this. Since then, there's all sorts of countries have continued producing nuclear weapons since then, and designs have drastically changed, and they're much more damaging today than they use multiple warheads. There's all sorts of things we don't really have time to get into, but yeah, they're much more dangerous today than they were then. Now, just to talk about it briefly, I don't know, have you guys, you don't cover this in social studies, it's not till next year. But, so why would the U.S. use a weapon that is so deadly? Like, do you know what the sort of reasoning or logic behind that was? Lillian?
Maybe like so they thought like before they attack next time they would think twice and be like, well if they attack the US might use something deadly again.
Yeah, so there is probably part of it. So they dropped these bombs hoping, so after the first bomb was dropped over Hiroshima, the U.S. is hoping that Japan would immediately surrender after seeing the force that these weapons had. They did not. Okay, they did after dropping that bomb on Nagasaki. Well, I don't know what the calculation was there, because what many people will say that were active at the time is the reasoning is that yes, are tens of thousands of people going to die when we drop this weapon? Yes, many of them innocent civilians. Yes, but if this war continues for a long period of time, people are dying at a drastic rate in the war itself. So if you like balance out, well, yes, a lot of people are going to die when we drop this bomb, but probably more people are going to die if this war continues another 9 months or another year. That's going to be greater, and so that's one way of sort of justifying the use of a weapon of that sort.
Didn't he almost get into a nuclear missile with Cuba? Like when Cuba came?
There was a threat of it, yes. All right, so luckily, this energy that we talk about being released in a nuclear detonation in a weapon can be controlled and can be used in a way that's more beneficial. And so nuclear reactors work on basically the same principles, where you have a nuclear fuel, uranium-235, which decays, releasing large amounts of energy. That energy is transformed into heat, which boils water, creating steam, and the steam spins a turbine, making electricity. The key here is that the reaction is controlled. And one of the ways that nuclear reactors do this is by using something called control rods. So what is it that really causes the chain reaction to continue? Like, what is the key part that we were just talking about? Michael?
So like when you hit the element with your first neutron, when it breaks off into the different elements, it releases neutrons, and those are what keeps the reaction. So if you stop that from happening, then you can stop that reaction.
Yes. By trying to control the release of those neutrons, we can control the rate of that nuclear reaction, that chain reaction. It's done with these things called control rods. Control rods are these things here. They move up and down. They're made of cadmium or boron, and they can absorb many of these neutrons. So if you put the control rods all the way down between the fuel rods, then basically the reaction slows way down because the neutrons that are released from this fuel rod can't instigate the next reaction in this fuel rod. So by raising and lowering these control rods, they can regulate the rate of the reaction. They're also a moderator, which is a substance, okay, typically water, that will slow down the neutrons that are released. The neutrons need to be traveling at the proper speed in order to initiate this breakdown, this nuclear decay. Okay, and so these moderators help that to happen. You know, a nuclear reactor works like any other power generation facility, with some exceptions. You know, like hydropower, like a hydro dam can generate electricity. A wind turbine can generate electricity. A coal-fired power plant generates electricity. And they all do it by taking spinning motion, where you have magnets spinning within a coil of wires, and that generates what? Electricity. That's what a turbine is. The spinning movement is used to generate electricity. So you could use water to spin the turbine. That's how hydroelectric power works. You could use the wind power to spin the turbine. That's how we generate electricity with wind power. If you have coal-fired power plant, you use the coal, you burn it, you heat up water to steam. As that steam rises, it's forced to spin a turbine. And nuclear energy works in the same way. The heat from these nuclear reactions turns water, okay, into steam, which goes through a turbine, generating electricity. Usually always now, the turbines are kept completely separate from the nuclear reactor. Okay? It's to prevent, if there's any accident with the turbine, it can't damage the nuclear reactor. There's all sorts of safety mechanisms in place because we have uranium fuel. If there was a meltdown, if things were not working properly, it could lead to serious situation. There's been a couple of those that we'll talk about. So overall, just to understand the process, we start with the heat that's given off by this nuclear reaction, which boils water, changes it to steam. That steam gets piped to a turbine, spinning it in order to generate electricity. It's really not that complicated. I'll answer questions in a minute. I just want to finish a couple things here and then I'll try and get to your questions. Now, explain. The uranium that's used in these nuclear power plants is packaged into pellets. They're tiny little cylinders, like a little bigger, I guess, than your pencil eraser, but about like that. Okay? This is what a uranium pellet looks like. And the amazing thing when you talk about the amount of energy contained, this tiny little pellet that you hold in your hands like this of uranium could generate the same amount of electricity as 3 barrels of oil, 1 ton of coal, or this giant tank of natural gas that you could hold in your finger. That's how much energy can be generated from nuclear energy. You know, a kilogram of uranium can produce 100 trillion joules worth of energy. That's about what you would get out of burning 4 million kilograms of coal. So that's a huge amount of energy. Now, there's a little bit of a debate, and I had this conversation with 2 women on Tuesday. We were when I was in Albany. Somebody referred to nuclear energy as clean energy. And these 2 women disagreed with that. I agreed with that. Why would I call nuclear energy clean energy?
Because pollution.
Good?
So it doesn't pollute? Doesn't make pollution?
let's be more specific. What does it not produce? Ian?
Greenhouse gases?
Yes, it produces 0 carbon dioxide. And if you've studied global warming, you know carbon dioxide is the main human contributor to global warming. And that's a major issue in our world today. So, yeah, so fission, energy generated by fission has some benefits. It produces 0 greenhouse gases. The fuel is relatively inexpensive in extraction, and it produces a huge amount of energy. Pretty economical once it's running. Problems, however, there are some major problems. It's extremely expensive to build a nuclear power plant. Okay?
Right, but in the long run, it will eventually work.
So high initial cost. It also results in radioactive waste. And that's why these women disagreed and did not see nuclear energy as a clean source of fuel, because it does. When those uranium pellets are used, they remain dangerous and radioactive. And we have no real good way of disposing of them. Basically, we hold them for a while, let them cool down, we encase them in concrete, and then we let them sit around. We have nothing to do, there's no way to remove the radiation from them, so they remain radioactive. There's proposals to bury them deep in a mountain that's in a geologically stable area and just let them sit there. Some people propose sending them to space, but there's really not a great way of getting rid of that radiation. This is what a nuclear reactor core looks like. This video shows it. I know we're not going to have time for it today.
Hey, it's Tim.
What were your questions? Somebody had a question.
You have